Swayam Prabha. Digital India. Educated India.
Okay, so in this module, we are going to talk about the topics related to velocity, acceleration, and angular velocity, namely the rigid body mechanics in general. So what we have are the topics of velocity, acceleration, and angular velocity of rigid bodies. Okay, so these are in broad sense is what we are going to talk about in the next few modules. So let me just emphasize the point that the mechanics of bodies course is mostly dealing with kinematics. Namely, we don't talk about this question of how the particle is moving. We mainly talk about, given the forces, how the motion of the particle is described, right? This question of how the particle is moving is mostly a question of dynamics, and listeners should look at my previous course of SwayamPrabha, namely the nonlinear dynamics for engineers and biology, on answering this question of how the particle is moving, right? So in this course, we will be mainly describing the motion of the particle. We will not answer this question of how. Okay, so so we are talking about the kinematics of the particle here. So it's a branch dealing with motion of the bodies without answering why the bodies are moving. Why bodies are moving. How and why the bodies are moving. Okay. So why the bodies are moving. Yes. Okay. So to begin with, we are talking, remember, this is a course of the mechanics of bodies. So we are primarily discussing rigid body dynamics. So what is a rigid body? So typically we can always define a body which is a non-particle system as a system of particles. So a rigid body could be defined as a system of particles which are connected with some, let's say, light rods. When I say light, typically I mean weightless, right? Or the weight of the rod is negligibly small compared to the particles that are attached to it. That is what I mean by weightless. Okay, so rigid bodies are collection of particles linked with a light rigid framework. Okay. So then what we have is, we look at, to begin with, we look at 1D motion, the straight line 1D motion, right? So we look at the straight line or the 1D motion. And what we have is, we are talking about the motion of a particle along a line. So let's say we have a particle P and it is moving with a velocity v, right? So to begin with, let us start by describing the mean velocity of the particle P, right? So we have a particle P we have a particle P moving moving over the interval from T1 to T2, right? And let us say we talk about the mean velocity. So the mean velocity of P is the displacement. We have already introduced the concept of displacement right in the first module. Is the displacement of P divided by the total time. Okay. So just the formula is that the mean velocity, we talk about the mean velocity as v subscript m. So the mean velocity is the position vector of the particle, at T2 minus the position vector of the particle at T1 divided by T2 minus T1. Okay. So that's the mean velocity. Okay. So then what we have is, let's continue our discussion here. What we have is now, we have already now started with the discussion on mean velocity. Similarly, we can discuss the concept of instantaneous velocity. So instantaneous velocity can be described from the mean velocity in taking the limit of the ratio, right? Limit where that interval of the time is approaching 0, right? So the definition of the instantaneous velocity is defined to be, I am not writing the entire statement, it's just defined to be v is d of x dt, right? So this is the same as the mean velocity in the limit when the interval of time is approaching to 0. So whenever we talk about velocity, we are talking about the instantaneous velocity. We are not talking about the mean velocity. So in our subsequent discussion, we always refer to instantaneous velocity when we only say velocity, right? And similarly, when we talk about acceleration, that is the instantaneous acceleration. So similarly, you have the concept of instantaneous acceleration as a to be equal to dv dt, which is d2 x dt2, right? And then what we have is, let us see what we have. So suppose let's look at one quick example just to get the idea of what we have spoken about. So suppose we have a particle, particle P, which is starting from point O at time t, right? So particle P which is starting from O at time t, and it has a position vector given by the following formula. So r is t cube minus 6t square plus 4, and what we have to find is, we have to find the velocity and the acceleration of P at any time t, right? And also from the same formula we have to show that P comes to rest twice, and we need to find the position and acceleration of P at the later time, of the two given times. Okay. 2 given times. So the problem says you have to find the velocity and acceleration and show that the particle comes to rest at 2 times, namely that the velocity of the particle becomes 0 at 2 times, and for the 2 times that we find where the velocity is 0, we have to find the position and the acceleration of the particle at the later of the 2 times. That is what the final part of the problem says. So when I talk about finding the velocity and acceleration, I just mentioned that we want to find the instantaneous velocity and instantaneous acceleration. So my instantaneous velocity v is going to be dx dt, and that is going to be 3t square minus 6t, and that's it, right? We have differentiated this formula for r. So this is a motion in 1D, and that is my velocity. And similarly, if you want to find acceleration, we differentiate this velocity to find the answer. Now most important is we have to show that the p comes to rest twice. So namely, we have to find the times when the velocity is 0, right? We see that from here we get t equal to either 0 or t is equal to, well, 3t cube minus 12t. So hold on. So this is a 12 here. So we have that t is equal to 0 or t is equal to 4, and for this 2 times the velocity is 0, and we have to find the acceleration and the position of the particle at this later of the 2 times. So we have to, the last part says find the position r at 4, t equal to 4, and the acceleration a at r at t equal to 4, and that's all what the problem needs us to find. So then let us look at a very similar problem to see, what are the other tricks involved. So here is another example. It says find the velocity and displacement of p whose acceleration at time t is a of t given by 12t square minus 6t plus 6, right? So now what we have to find is, well, we need to give some conditions as well, such that p is initially at point x equal to 4 meters. So this is again a problem in 1D, and moving with velocity 8 meters per second. So what is given in the problem is the acceleration, and we need to find the velocity and the displacement. So this is a problem which is the reverse of the previous problem, the reverse exercise. Namely that we are given the acceleration and we need to integrate to find the velocity, and again integrate to find the displacement. And at each level of integration, we are going to involve a constant of integration which will be found using the initial conditions that are given in this question. And I think that is where we leave. I think the listeners can quickly find the solution. So using integration twice. So problem involving integration. So this is, I leave it to the listeners. Okay. So that can easily be done. Okay. So then let us start our focusing our attention on problems in 3D or in general space, in general Euclidean space, by developing the so-called frames of reference, the concept of frames of reference. Okay. So to begin with, we are starting our description of general motion of a particle in 3D, general motion of the particle in 3D, and let us say let us say that we have a particle, let's say a particle P, and now we describe the position vector of P with respect to some coordinate axis. So let us say our coordinate axis is I, J, K, and the coordinate axis has an origin O, and from O we define a vector extending to the point P under consideration, which is the vector OP. Okay. So, so let us say that the position vector, so I am just writing what I just said. So let the position vector of P with respect to the origin O, right? The position vector of P with respect to the origin O of a rigid reference frame F be R. Okay. So let us say that this position vector is R. And now we need to talk about this briefly about this reference frame we are talking about, right? So this reference frame where we have introduced this F. So a rigid reference frame is a rigid body with the origin O, right, as the origin of the body. So that's it, and also it is associated with a set of 3 unit vectors serving as its coordinate axis. So a rigid reference frame let's say this curly F is a rigid body. It's a rigid body with a point O as the origin of the body, and the unit vectors I, J, K as the vectors along its coordinate axis. So hence we denote our rigid reference frame F with as a function of F O I J K. So when we have all these 4 quantities, with these 4 quantities we can quickly define a reference frame, that is the origin and the 3 coordinate axes which are the orthonormal vectors. Okay, the coordinate axis consisting of the 3 vectors which are orthonormal. So so what have we got? Let's look at a quick example. So the problem says relative to the frame F, let the position vector of P at time t is given by R of t is equal to 2t square minus 3i plus 4t plus 4j plus t cube plus 2t square k. Okay. So relative to the frame F, the position vector P of at time t is given by this formula. Okay. So what we have to do is we have to find the position vector OP at time t equal to 0. That is the initial position vector. And then the next part of the problem says you have to find the velocity of P at t equal to 1. And finally, the third part of the problem says you need to find the acceleration of p at time t equal to 2, right? So all these parts should be fairly straightforward, given the fact that we are talking about instantaneous velocity and instantaneous acceleration, and the listeners can quickly differentiate to find these values and plug the parameter. For the position vector, the parameters are t equal to 0. For velocity, it is t equal to 1, and for acceleration, t equal to 2. Okay. So briefly, I want to digress, in our discussion by just trying to highlight what do we mean by, what is the interpretation, or what is the geometric interpretation of velocity and acceleration. We talk about the geometric interpretation of velocity and acceleration. Okay, so the geometric interpretation of velocity and acceleration, and so let us see what we mean by that. So our velocity, we have defined our instantaneous velocity to be dr dt, right? T being the parameter, typically time, which is the scalar parameter, and suppose now let us say we introduce a new parameter being the arc length. So we have, let S being the arc length traveled from the origin O. Okay. So we assume that the particle is moving along a curve defined by this position vector r of t, right? R of t. And the distance traveled along the curve is said to be the arc length, S. Right? And what we have is that V is dr ds by chain rule times ds dt. And what we have is that, notice that dr ds, the way we have described dr ds is the rate of change of position along the arc length, and this is going to be the speed of the particle or the magnitude of the velocity. So we have that this is going to be the speed of the particle, which is the magnitude of the velocity, or simply I talk that this is v without any arrow. And then ds dt, that is the rate of change of arc length with respect to t, is nothing but our tangent, right? T of s, right? So what we have is our instantaneous velocity is the speed along the tangent direction, right? So what we have found from this simple exercise is that the velocity always acts tangent to the curve. The velocity always has a direction which is tangent to the curve, right? And its magnitude, of course, is the speed. And then, so along the tangent to the curve. And then we have that a, the acceleration a is dv dt, and now notice now that this a is d dt, which is v of t, right? So we have that we have just plugged in the formula for velocity here, and notice that this is going to be dv dt times t and plus v times dt dt, okay, using chain rule, using the product rule. So what have we got here is that this is also equal to v dv dt is change of speed with respect to time. So let us call this as v dot. So v dot along t, the tangent direction, and plus what we have is that v times dt dt. So dt dt can be written as dt ds times ds dt, and what we have is that this quantity, so v dot t, and then this is what we have. Okay, so notice that dt ds, well, what have we got? ds dt, this is nothing but the change of arc length with respect to the time, and this is our speed. And dt ds is nothing but, from the definition of curvature, this is equal to curvature times the normal vector. So finally we have a formula that this is equal to v dot times t plus kappa v square times n. So notice that the two components of the acceleration are the change of speed which acts along the tangential direction. So this is the tangential component. And here the second is the normal component which acts normal to the curve. Okay. Okay. So what we have is for uniform, let us look at this. So this is what we have, what I wanted to convey when I said about the geometric interpretation, right? So the normal and the tangential components of velocity. Okay, so let us look at a special case where the particle is moving along a uniform, a circle of fixed radius, or the so-called uniform circular motion. Okay, so uniform circular motion. So what we have is motion with constant speed. So when I talk about uniform, it means motion with constant speed. And the particle P moves counterclockwise. So I am assuming that the particle P moves anti-clockwise, with speed u, right? So what we have is, notice that we have a circle with origin O, and we have that the O has the radius, let's say the radius of the circle is fixed, and the particle P is moving counterclockwise, right, with speed u, right? So it's a constant speed, it's a uniform motion. Okay, so then let us say this is our particle P, and at any given time the particle P is extending an angle theta at the origin, right? So now what is theta here? So theta is the total length of the arc which is moved at any given time, which is u times t, divided by the length of, that is the radius, divided by the length of the radius, which is b. So so we see that the motion of the particle P along a uniform circle, that is the uniform motion, can easily be defined using, so r is nothing but b cos theta I hat plus b sin theta j hat. So these are the components, the x and the y components of the position vectors at any given time. Now from here we can replace our variable theta in terms of the variable t, because t is the real independent variable. So we have that r is b cos ut by b I plus b sin ut by b j, right? Okay. So then what have we got? What have we got is that v, well, to find from here, to find the velocity v is going to be dr dt. So that involves a simple differentiation, and we will see that this is going to be u times, we use the composite rule, u times sin ut by b and with the cos it gives you a minus sign plus u times cos ut by b, which is j. Okay. So we can simplify this a little bit more by noting that this is equal to u times cos of this angle j minus sine of this angle I, right? Similarly, we can find acceleration. We can see that the acceleration is minus u square by b minus u square by b times cos of this angle I plus sine of this angle j. Okay? Okay. Notice that this quantity is the same as your vector r, right? Notice that r, so r was equal to b times r hat, or r, well, I must introduce, try to differentiate this r with this r. This is the unit vector. This is the unit vector, okay, along the r, along the radial direction, right? So notice that my position vector r is b times r hat. So notice that my acceleration now here is minus u square b times r hat. That is, the acceleration here acts along the radial direction and it has a negative sign, which means it acts along the radial direction towards the origin, right? And now v, notice that v is, well, similarly v is, can we do something? We can change this cos to sine again using by subtracting with pi by 2, and we see that again v is you know, it's 90 degrees lagging than a. So so from here we find that the magnitude of v is u, and from here we find that the magnitude of the acceleration a is u square by b. Okay. So what have we got here is that, notice that our motion along this circle was such that the speed u was constant. So u is a constant, right? And so which means that notice that the acceleration has just one component, which is along the r direction, or r hat is the normal direction, So if we go back a few slides, go back one slide, notice that the acceleration was v dot times the quantity along the tangential direction times the quantity along the radial, the normal direction. The normal direction is the radial direction. So the quantity along the tangential direction in uniform circular motion is 0, because it's a motion with constant speed. So v dot is 0, and the quantity along the normal direction is kappa times v square, right? So we see that this is kappa times u square, u being the speed of the particle. So from here we can quickly deduce that the radius, the curvature of the system, the curvature of this curve, the curvature of this curve is given by kappa, which is 1 over b, right? Curvature is 1 over b, just comparing the formula. Okay, so now let us generalize this result for a more for arbitrary motion in arbitrary space, whether it's 2D, whether it's 3D, it doesn't matter. So let us generalize this system.